Hi, I am Banerjee, a professor in the Department of Physics at the Indian Institute of Technology, Kanpur. These are my collaborators, Mr. Gorky Shaw and Mr. Pabitra Mandal, my PhD students, and Professor Tamegai from the University of Tokyo. The relatively lower density ordered vortex solid phase in superconductors melts into a higher density disordered vortex liquid phase under the influence of enhanced thermal fluctuations. Shown below is a schematic representation of the behavior of the shear elastic moduli of the vortex lattice as a function of increasing magnetic field. Vortex melting is expected whenever the vortex lattice is soft, namely when the elastic moduli is low at low and high magnetic fields. At low magnetic fields, theoretically a transformation from the vortex liquid to solid phase is expected due to the enhancing stiffness of the lattice due to increasing intervortex interactions with increasing magnetic field. In the present study, we have investigated the nature of the low field vortex phase. High field melting is an already well studied phenomenon. Using the high sensitivity magneto-optical imaging setup developed at IIT Kanpur, we measure the local magnetic field distribution inside the superconductor. Shown here is a schematic of the local field distribution across a superconductor due to the presence of vortices in it. The local magnetic field is proportional to the density of vortices in the superconductor. We measure the local magnetic field distribution inside the material by measuring the intensity of the Faraday rotated linearly polarized light. In our experiment, we have attempted to measure the changes in the vortex density due to phase transformations in the vortex state at low magnetic fields. These are differential magneto-optical images captured at 50 Kelvin, which represent the changes in the local magnetic field produced in response to an external field modulation of 1 Gauss, which is applied at each of the measuring applied magnetic fields. Note the bright white regions in these images corresponds to vortex liquid puddles where there is a comparatively larger change in the local magnetic field or vortex density. Our investigations show an initial low field vortex liquid phase which sustains larger changes in the vortex density, settling down into a vortex solid phase at higher magnetic fields which sustains smaller changes in the vortex density. Furthermore, nucleation of the vortex solid phase is characterized by the disappearance of shielding currents within the vortex solid regions, as is noted within the encircled region and also with this arrow. Based on such studies, we have identified the vortex liquid to solid melting line experimentally. This experimentally determined phase transition boundary is also matching well with the theoretically predicted melting line at low magnetic fields in pin-free superconductors. Around this melting phase boundary, we have also identified a regime of coexistence where the vortex solid and liquid phases coexist. Using our magneto-optical imaging technique, we spatially resolve the information on relaxation of remnant magnetization at different locations in the sample, which we use to deduce the pinning landscape across the sample. The variation in pinning across different regions of the sample are represented by the colored bar present beside the color image of the sample. We find that the location of the low field vortex liquid to solid phase transition boundary shifts with variation in pinning, which is well described by the effective Lindemann number increasing with the pinning strength. Thank you.